The previous video modeled growth using an exponential function. This video will model heat with an exponential function. So Newton's law of cooling gives you an approximate temperature of an object. So Newton's law of cooling says that the temperature at time t of a cooling object can be modeled by the function f of t, which is capital T plus a shifted exponential function, e to the a t plus b power. Here, this capital T is the surrounding temperature, and A and B are constants that depend on what's heating or cooling. The surrounding temperature affects how fast something cools. If you want something to cool off faster, you could put it in the freezer and it'll cool off faster. If you want it to not cool down, you could put it in an oven. So the surrounding temperature definitely affects how fast something cools off. A and B are constants that depend on the material property of what's heating or cooling. So if you want to cool off marshmallow cream, it's going to have a different rate of cooling than if you want to cool off melted steel. Let's see an example using this Newton's law of cooling. So let's say a turkey is cooked for Thanksgiving, and it's taken out of a 300-degree oven. So the turkey is 300 degrees initially, and placed in a 75-degree room to cool. 1 hour later, the temperature is taken. So 1 hour later, the temperature is, let's say, 150. So it took an hour to cool off halfway. And my question is, when will it be 100 degrees? So this model that we're using to determine how fast something cools off has three unknowns. It has T, A, and B. We need three pieces of information to decide what those constants are. So I straight up tell you what the surrounding temperature is. It's in a 75-degree room, so that's capital T. And I'm going to use this other information that it starts at 300 degrees and is 150 an hour later to determine A and B. So let's do it. I have that my model at this point is 75, that's the surrounding room temperature, plus E to the AT plus B. I also know that initially at time 0, it's 300 degrees. So initially it's 300, therefore 300 would have to be 75 plus E. I'm plugging in T equals 0, so it's simply E to the B. You could subtract, you get 225 is E to the B, and then you could take logarithms on both sides to get log of 225 is equal to B. So I've identified B. I also need to identify A. I know that after 1 hour, so when time is 1, the temperature is 150. So 150 should be 75 plus E to the A times 1 plus B, which now I know is log 225. I could solve this equation for A. I could subtract 75 on both sides, so I get 75 is E to the A plus log 225. The way to solve equations that involve exponential functions is to isolate the exponential function and then undo the exponential function by applying the logarithm on both sides. So if I do that, I get natural log of 75 should be a plus log 225. So at this point, I can find a is log 75 minus log 225. And if you remember properties of exponents, we've seen this trick a little bit when you have the difference of two logarithms that turns into a ratio or a fraction, 75 over 225. So that's 1/3. So log 1/3 is equal to a. So I have a, I have b, I have capital T. So my model is now f of t, which is 75, plus e to the log 1/3 t. Log 1/3 was my a, so a times t, plus b, which is log 225. This is a good answer, but I'm going to write it in a slightly different form just because I see I have e to log powers. So I could simplify a little bit. This is e to the log 1/3 to the t power. So here I had t times a logarithm. I use that property that now I can turn multiplication into exponentiation like this. I have e to these two terms. I'm going to write it as e to the first term times e to the second. And the final way to rewrite it could be 225 times 1/3 to the t power. So that's my model. Let me graph this function to give you an idea of what this looks like. So what we're saying is, initially at time 0, the turkey is 300 degrees. And in 1 hour, so let's say 1 hour, it's half as hot, so it's 150 degrees. So it starts up here and then it goes down here. And long term, it's going to be 75 degrees. If you think about the situation, the turkey's never going to get colder than 75 degrees. And as time goes on, it's slowly going to approach that temperature. A here is 1/3. Log of 1/3. Log of 1/3 is a negative number. So I have e to a negative exponent. A is negative. That means if t is a big number, this is close to 0 because e of a very negative number is small. What I'm trying to get at is that 75 is a horizontal asymptote of this function, and this function decreases, the temperature is going down, and it decreases exponentially towards 75. So that's the sketch of this graph that we're using to model. Now, maybe we should answer the question to finish the video. When will it be 100 degrees? Well, I want f of t to equal 100. So what that tells us is that 75 plus 225 times 1/3 t is equal to 100. You can subtract 75 on both sides. This will be 25. You could divide both sides by 225. I think if you do that, 25 over 225 is 1/9. So you get 1/3 t is 1/9. If you can't see that t is 2 from this step, you could take log on both sides and solve. But this, I believe, tells me that t is equal to 2. Okay, nice.